Hello everyone, in this theory seeker tutorial number 44, we will review how the space charge is created when P and N regions are close together and the built-in voltage across the junction. We will also review the contact electromotive force, and we will finish with the contribution of Russell Ohl on the solid-state electronic development with its invention list. In this slide, we can see both three-dimensional silicon crystal with P and N doped far away from each other. Now we will see what happens if the doped P and N are close to each other. When P and N doped are closed, immediately the free electron with high energy in the N doped silicon will move to the lowest energy position provided by the lack of electron or hole in the valence band. Again, to do an analogy with human behavior, the free electron can be replaced by a stand-up human, which is looking for a position with less energy, like sitting in the chair. But as the free electron moves to the hole, in the N-doped area, a negative electric charge is missing with 4 electrons instead of 5. So, close to the phosphorus atom, a positive charge appears. It is the opposite on the p-doped side. An additional electrical charge is present with 4 electrons instead of 3. So, close to the boron atom, a negative charge appears. Those positive and negative charges are called a space charge because those charges are linked with a space. They cannot move. In this slide, I represented a p-doped semiconductor in the left side with boron as Na acceptor atoms and the N-doped semiconductor in the right side with phosphorus as Nd donor atoms, the plus, minus, and hole representing just the acceptor and donor atoms. For the p-doped, the red plus sign represents the 5 protons of the boron nucleus, the blue minus sign represents the 5 electrons, and the circle represents the lack of electron in the boron external shell. Of course, the electrical charge is equal to 0. For the N-doped, the red plus sign represents the 15 protons of the phosphorus nucleus. The blue minus sign represents the 15 electrons spread in 14 electrons, including the 8 electrons of the full external shell plus 1 free electron. Of course, the electrical charge is equal to 0. Now we move P and N-doped material close to each other to create what we called a PN junction, shown by the red vertical line. As we said in the previous slide, when a free electron with high energy is close to a position where the energy is lower, will move to this position. The free electron of the phosphorus atom will move to the low energy position available in the boron atom. The missing electron close to the phosphorus will generate a positive charge, and the additional electron close to the boron will create a negative charge. In the positive and negative space charge, there are no free electrons, which means that we are in the same configuration than intrinsic semiconductor, all electrons in the valence band and no electron in the conduction band. The positive and negative charges create an electric field with a maximum field at the PN junction. The N-doped side increases its voltage compared to the p-doped side. This is called the built-in voltage. This process can be continuing with other electrons, which will increase the electric charge, the maximum field, and the built-in voltage. This process will continue until the internal junction voltage will force the electron on the N-doped side to stay in the N side. This built-in voltage, VBI, is equal to 0.6 volt at room temperature for the silicon 0.3 volt for the germanium and 3 volt for the carbon. This area with positive and negative charges on each side of the junction is called the space charge. Of course, the distance depends on the doping concentration. In this slide, the space charge is symmetrical because I assume that N and P have the same concentration. But in real doping, one doping is generally higher than the other one. With 10 to the power of 18, the space charge width is 0.03 micrometer, but it can be higher if the doping concentration is 10 to the power of 14. Those space charges cannot move because the charges have attached to the donor or acceptor atoms, and no free electron in this area. Those charges look that charges trapped in the dielectric element as a capacitor charge. Now we will explain why if we measure a p-n junction diode with a voltmeter, we will not measure 0.6 volt. On the TRICR tutorial number 43, we compared the free electron in a crystal with a gas molecule in a volume following the perfect gas law PV equal nRT. Each conductor has their own equivalent electron pressure. Different conductors will have different electron density, which means different pressure of the electron gas. So if the metal 1 has a pressure PE1 and the metal 2 the pressure PE2, if the pressure PE1 is higher than PE2, some electron of the metal 1 will move to the metal 2, as molecule will do in a gas. Those electrons will create what we call contact electromotive force. Between two different metals A and B, if the metal A has electron pressure higher than metal B, some electron will move from A to B metal and will create a contact electromotive force. Of course, this electromotive force VA minus VB between those two metals is very low, as few millivolt. Of course, in a p-n junction, the electron pressure in the n side is much higher than the electron pressure in the p side, so the contact electromotive force is much higher than both metals. Between metal to p-doped material contact, of course the electron pressure in the metal is higher than in the doped p material, so Vm is greater than Vp. Between metal to n-doped material contact, electron pressure in the n material is higher than in the metal, so Vn is greater than metal voltage. The sum of those contacts voltage gives 0 volt. This is why when we measure a diode with just a voltmeter, we cannot see the built-in voltage of 600 millivolt. For a p-n junction, the built-in voltage is equal to 600 millivolt. For a Schottky diode between metal and n-doped type, the built-in voltage is less than 0.3 volt. Now we consider three different types of metal, A, B, and C. Junction C to B is plus 1 millivolt, red line. B to C, minus 1 millivolt, dotted red line. Junction B to A is plus 2 millivolt, blue line, and A to B, minus 2 millivolt, dotted blue line. Junction A to C is minus 3 millivolt, dotted green line. If we start at 0 volt on the right side and turn counterclockwise, we will get plus 1 millivolt, then plus 3 millivolt, plus 1 millivolt, 0 millivolt, plus 1, plus 3 millivolt, then 0 millivolt. So after crossing all contacts, the sum of the contact electromotive force is equal to 0 volt. I am very happy in this TRICR tutorial number 44 to talk again about Russell Ohl, because of course he is less known than inventors of the point contact transistor, but he brings a lot of contributions to the solid state electronic. Russell Ohl understood that impurities inside the semiconductor crystal plays a key role. He showed that increasing the silicon purity helped improve their detection ability in the silicon rectifier as a radar detector. On February 1940, he tested a small silicon slab that produced strange, surprising results. When exposed to a bright light, the current flowing through the slab jumped appreciably. He also noticed that different parts of the crystal produce opposite electrical effect when tested with a cat's whisker style probe. Ohl and his colleague Jack Scaff found that a seam in the slab marked the separation of the silicon into regions containing distinct kinds of impurities. One impurity, the element phosphorus, produces a slight excess of electrons in the sample, while the other, boron, led to a slight deficiency, later recognized as a lack of electrons or holes. They called the region N-type for negative and P-type for positive. The surface of barrier where this region met became known as a p-n junction. Light striking this junction stimulated electrons to flow from the N to P side, resulting in electric current. Ohl had discovered the photovoltaic effect that powers today's solar cells. His work was only understood by a handful of scientists in the organization, and one of them was Dr. Walter Brattain, which is one of the trios who invented the transistor in 1947. The p-n junction became the most common form of the rectifier used in the electronics industry and has since become a fundamental building block in semiconductor devices. William Shockley's conception of the junction bipolar transistor in 1948 derived from Ohl's Chen's p-n junction discovery in 1940. I am pretty happy in this video to highlight Russell Ohl because, from my point of view, for all the above list of its contribution in the solid-state electronics, he deserved the Nobel Prize. I want to thank you for your attention. On my next Seeker tutorial number 45, we will talk about the photovoltaic effect discovered by Russell Ohl. So see you soon and stay tuned.